beginner's guide to start with model railroad wiring. Like a pro? Well, that doesn't make any sense. But it does. If you're starting or planning to start with a new digital railroad, I'll show you how you can do that from the beginning, like a pro. Hello and welcome to Trends and Dioramas. My name is Chatterjee, and if this is your first time here, then do not forget to check my channel and hit that subscribe button and the bell icon so that you can take part in my adventures of making model trains, miniatures, dioramas, and various other scale model projects. I'm really excited about this because in a few months' time, I'm going to start building a brand new model train layout. Now, before all hell breaks loose, I'm going to start building small prototypes to test my design, components, and build essentials before the main project. Now, most beginners learn through trial and error. That's how I have learned, and to be honest, still learning. Now, there are lots of experts, videos, model train forums, but when you're a beginner, most of that doesn't really help because you do not have the big picture and you do not have the hands-on experience. But if you follow some basic techniques, you can install most of the electrical and electronics components in phases, stretching your time and managing your budget efficiently. And if you really plan well, you will never have to redo anything that you have done. Yes, even after years, you might be installing new techniques, you might be installing new hardware and software, but the existing installations of your track and wiring will still hold good. Sounds interesting? Let's get started. Here is what I've started with. A plain 60-inch by 10-inch piece of board with a simple runaround track and a fork. The objective of this is to create a prototype for wiring and electronics, so we'll be skipping the track laying part. Here, tracks are simply pinned down to the board and not even glued. The turnouts did go through appropriate modifications though, but more on that in a separate video in the near future. The entire construction was completed over a weekend, and by late night on Sunday I did have a fully functioning digital railroad with trains running. For this board, most of the wiring will be done on top of the baseboard so that it's easy to see and connect the dots. There would have to be some under the board installations, and I'll do my best to make it as clear as possible with verbal explanations. Now before we start, let's clarify a few things. I'll not be covering soldering and turnout modifications in this episode, but yes, there will be dedicated videos to cover those aspects that will complement this video. I'll be in the Digitrax house for the overall system, but there will be instances where I'll be using non-Digitrax products. For an example, all my switch machines are going to be Cobalt IP digital that runs off DCC bus and not through LocoNet. If you do not know what LocoNet is, stick around, it will be covered in subsequent videos. Also, the basic wiring described in this video is not dependent on which system you use. The wiring and techniques we'll be talking about today can be used for any DCC system. I want to achieve complete automation using a computer for my upcoming layout, and I want to unravel the secrets of that using this small prototype. The signaling system will be speed signaling and not position signaling. If you don't know what I'm talking about, then again, this will be covered in subsequent videos. Just know that the Digitrax system is designed to achieve position signaling and not speed signaling, so I'll have to modify the purpose of the system to suit my needs. I have no clue if I'll be successful, but hey, that's the learning that I've signed up for. So, what are some of the basics that real railroads follow? Let's review them quickly. The way real railroads control their trains is through means of blocks, which literally means a block of track isolated from the adjoining track or tracks and electrically or electronically connected to provide a feedback of occupancy to the controlling system, either CTC or ABS. Typically, in a straight line of track without any divergence, the track is divided in multiple blocks with signals at each end of each block protecting them. In real life, these individual blocks are often several miles long. Since trains are long and immensely heavy, they often take miles to jump up and down the speed range or come to a stop. So the signals tell the engineers what to do based on the status of not just the immediate next block, but also 1, 2, or more blocks ahead. Things get complicated when there is a switch in between, in signaling term, what is also known as a divergence. The signals then will have to tell the engineer which route they are supposed to take, and in case of speed signaling system like the one I am trying to model, what speed they should be at. In a scenario like that, a switch or a combination of back-to-back switches needs to be handled as a separate entity, in signaling term also known as a control point or CP. Often these switches and the blocks that they serve need to be interlocked. An electromechanical means to ensure only the right combination of switch throws are possible to create a passable route for a train. This is considered as the basic and most critical safety measure in any railroad across the globe. Now, we will create all that in this tiny piece of board. Yes, all of that, just in smaller scale. The reason I explained the theory behind it is just to give you an idea of what I'm trying to achieve here. The pro part in the beginner's guide of DCC wiring is to give you an idea about how to get some basics right so that you can keep building on the base infrastructure as you grow. Now that we know the basics of a real railroad at a very high level, let's take a look at our baseboard to reveal the very basic wiring of a digital model railroad. This might seem like a lot for such a small layout, but I can guarantee you that it's not. This is a very basic wiring that every digital model railroad should have. And it is really easy once you understand the principle behind it. Now let me explain the system to you in as simple words as possible. You see, there are two pairs of thicker red and black wires running along the two long edges of the baseboard. These are my bus. They are the main communication system to transfer data between the command station and any component on the railroad. I have named the red one as rail A and the black one as rail B to denote which terminal of the command station the wires originate from. For a medium or large railroad, these wires should be as thick as possible, at least 14 AWG, 12 is better. What I'm using here is a little thinner, 16 AWG, because this is just a 5-foot long railroad, that should suffice. Then you see several thinner red and black wires from the two rails connected to the respective red and black bus wires. These are my feeders. These should be at least 20 AWG for an HO railroad, and it's better that they are not more than 6 inches long. They are meant to distribute the signal from the bus wires to the rails, or to accessories like in my case the switch machines. Here when I say signal, what I mean is more like a constant exchange of data packets between the components. If you're thinking why there are two sets of bus wires, then you're asking the right questions. In my next video, I'll be showing how to create power sub-district and short circuit management using Digitrax PM42. The two sets of wires that are now connected in parallel will be isolated through that hardware. I just planned and made the wiring to accommodate that so that when I install the PM42, it will be nearly a plug and play. Coming to the feeders, you might find that there are more black wires than red. The reason being, each black wire from rail B bus are connected to an electrically isolated piece of track called a block. The isolation is done through a pico insulated rail joiners. It's a little harder to see, so the red markers show the break in the line. Right now, these wires are directly connected to the rail B bus, but in the subsequent videos, you will see that they will be powering the rails through a block detector hardware, either Digitrax BD4 or BDL16. I learned the hard way that extensive labeling is one of the most important aspects of electrical and electronics work. Here you see that each bus wire is labeled rail A or rail B in their respective red and black colors. Also, each terminal shows which side is rail A and which side is rail B. On the tracks, you can see which rail is connected to rail A and which rail is connected to rail B. For this test bed, the visible black and red wires underneath the track makes it very easy for you to identify how to wire a railroad. Labeling your track itself during the wiring phase might be a very good way to achieve right wiring the first time. The connection to the switches is specifically labeled where S stands for switch and the number denotes its DCC address. Like in this case, this is switch number 101. These wires are connected to the switch rails. The connection to the switch machine is denoted as SM. These wires are connected to the DCC input of the switch machine, in this case, Cobalt IP Digital. In case it's not clear, when I say switch 101, that address is set in the switch machine. I labeled the connection to the switch rails with the same number for easy identification. So every switch essentially will have two connections. One is for the switch rails, denoted as S and then the switch address, and then for the switch machine, denoted as SM and the switch address. Both will be connected to their respective rail A and rail B bus wires. Therefore, planning is important. Imagine a scenario where this is not a test bed and a real model railroad module, and I have not planned about power management or block detection and laid the tracks permanently. That would result in a lot of rework on the basics when I decide to install power management or block detection, rip up the track, cut gaps in the rail, do additional soldering, redo a lot of work, and it's an overall a huge mess. And I can tell you from personal experience that that is a huge pain in the ass. Now in this approach, it would be much more time consuming at first during the planning phase. But basic wiring and the track wear aligning with your end goal, the future components can be added without touching any existing track work or even electrical wiring if you're using spring-loaded terminal blocks the way I'm using here. Now back to the test bed. The rail A is essentially common across the blocks. That is, this side of the line is shared by all blocks. Now why did I put so many red feeder wires? Because my tracks are not soldered with each other and I didn't want to rely just on the track joiners for power distribution to the next rail section. Even if you're handling much larger track sections and with soldered rails, occasional feeders are always a good idea, especially if the track sections start increasing in length. Most master model railroaders recommend 1 meter distance between each feeder. The switches, of course, are a little complex, and I'll make a separate video just on wiring and modifying a switch in the coming days. Just to give you a quick overview, these two switches, S101 and S102, are Pico electro-frog turnouts and they make a crossover. Whenever you're using electro-frog turnout to make a crossover, both the rails need to be isolated. Why? We'll come back to that shortly. Switch 103, however, is a micro-engineering turnout. Out of the box, they have an insulated frog. But given they are metal frogs, it's easy to power them. Notice that there are two additional wires between the frog rails and the stock rails that you didn't see in the electro-frog turnouts. Now if you're scratching your head, not to worry, I'll explain the differences real soon. Out of the box, the Pico electro-frog turnouts act like a typical electrical switch. In our case, if I hadn't made any modifications, when the switch is closed, the entire frog section would be connected to rail A sides. That means all these tracks would be connected to rail A. Now when the switch is thrown, then the entire frog section will be connected to rail B side. That is, all these rails would be connected to rail B. Now all that is fine, except that entire electrical connection would be dependent on this spring-loaded throw bar and about this 1 square millimeter area of contact. It's just a matter of time before these electrical contacts through this 1 square millimeter area and the spring-loaded throw bar might become unreliable. So we modify an electro-frog switch by the following steps. Isolating the frog by cutting the connection between the closure rail and the frog. Pico provides a very convenient way to do that in their newer turnouts by providing two easy-to-cut wires on the underside. They neutral power to the closure rails from the adjacent rails by adding a jumper. Pico also provides a gap in their webbing to make this job easier. Finally, we powered the isolated frog using an electrical switch connected to the switch machine that keeps changing the polarity of the frog depending on which side the switch machine is thrown. In our case, when switch 102 is closed, the frog remains connected to the rail A. When it's thrown, the frog changes polarity to rail B. Most modern switch machines, including the very cost-effective manual ones, offer some sort of electromechanical device to change the frog polarity. I'm using Cobalt IP digital machine, so for me it's just a matter of attaching the frog power line to the right port, and the switch machine takes care of the rest. For Pico electro-frog, the frog rails are actually one single piece connected to the frog. So whichever polarity the frog is in, the rail carries the current till you break the connection by introducing an electrical gap. So both the frog rails must be isolated with the connecting rails using insulated rail joiners, irrespective of whether you're making a crossover or not. Because of this, whenever you make a crossover using two electro-frog turnouts, you must isolate both the rails, because the frog rails of one switch and the stock rails of the other might have different polarities depending on the switch position, and if they're not electrically isolated, they will instantly short your layout. That's why you see a complete isolation between these two tracks. Another way to look at it is that going by the previous rule that both the frog rails of an electrofrog turnout must be isolated from the adjoining tracks, that actually puts an isolation between these two tracks automatically. Why? This is the frog rail of this turnout, whereas this is the frog rail of this turnout. So whenever you're making a crossover, you have all the four tracks with an insulated rail joiners. The frog rails of turnout 1, in our case S101, and the frog rails of the other turnout, in our case S102. Now coming to S103, this microengineering switch has an insulated frog out of the box. These tiny little gaps that isolate the frog from the closure rail and the frog rail make this frog electrically isolated from everything else. Not just microengineering, most switch makers apart from Pico make their switches this way. Previously, these frogs used to be made of plastic, making it impossible to power them. But with metal frogs, now these modern switches can be powered the same way we have done for the Pico switch. However, since the frog is isolated from the frog rails, the power applied to the frog will not carry over to the frog rails. Hence, you must put jumpers from rail A and rail B to the respective frog rails to ensure the frog rails have power too. So electrically speaking, you really do not need any insulated rail joiners if you're using this type of turnout, because the frog is electrically isolated from everything else. In fact, you can pretty well solder these joints and pull power to these rails directly instead of putting these jumpers as well. Even if you're building a crossover, you don't necessarily have to put any isolation between these diverging tracks and these set of tracks here, the way we have done it for Pico electrofrog turnout. You can simply join these tracks using normal rail joiners, solder them, and just solder your feeder wires right here, and that should work absolutely fine. So the question is, why do I have these rails segregated? Now that has nothing to do with turnout wiring. The reason I have this rail segregated is because this belongs to a different block, and these rails are segregated because they will belong to a different power subdistrict. Now, even if you consider a crossover, and electrically there is no need to segregate or separate these rails as we have seen in Pico electrofrog, in the end of the day, if you really want to do some advanced things like block detection, signaling, etc., you might end up segregating these tracks anyway. So more on that later in future videos. Switch modifications, turnout wiring, and switch machine installation are possibly one of the most problematic topics for the beginners in the hobby. So I'll be making a separate video focusing only on that topic in the coming days. Make sure that you hit that subscribe button so that you do not miss the notification when that video comes out. So to summarize, this is where I am at today. I have two sets of bus wires for two upcoming power subdistricts. The rail A connection to the booster is denoted by the red wires, and the rail B connection is denoted by the black wires. Notice that I have created labels for both the rails in the same color code. Rail A is common across all blocks within a power subdistrict. If that last statement confused you, stick around for the next episode in the Beginner's Guide series, where I'll talk about creating power subdistricts. Rail B is used to isolate the detection blocks. Though there is no block detection hardware is in place today, I planned it ahead and divided the blocks while laying the track by means of insulated rail joiners. I'll cover this in detail in an upcoming video about block detection. I will be using extensive color-coded labeling for each of the electrical components. As explained already, each rail, each terminal, and each component will be labeled and color-coded. You know what I'm thinking? Enough talk. Let's run some trains. In this up session, I'll simply swap the two trains, put my 280 consolidation in place of the G45 toner and the boxcar, and bring the boxcar to where the steam engine is. You see, I now have a fully functional layout, and frankly speaking, building the layout took much less time than producing this tutorial. I can now run trains for as long as I want before moving into power management and block detection. But whenever I decide to take on these enhancements, it will be much easier for me to do so since the groundwork is already done. In next episode of Beginner's Guide, that's exactly what I'll explain. Till then, happy railroading!